Good afternoon, everybody who missed class today. I just wanted to record a quick video to talk about a little bit of what you missed in class today. So first thing was correcting the homework. This is the key that I handed out in class. There is a PDF version of this on our haiku page, so you can go ahead and correct your work and show that to me. If you want to grab this tomorrow and do that over the weekend instead, that's fine, but I do want to check and see you've done your homework, and I want to take a quick look at it to see how you're doing on it. After that, we went through this question today. What is the difference between a balance and a scale? What are they measuring? So I'm going to talk about that really quickly with you. Set this here, see if we can do that. Okay, so the difference between a balance and a scale is a balance like this is comparing mass, whereas a scale over here is measuring weight. Notice that I use the words mass versus weight. Comparing means that you don't necessarily know an actual number. For example, if I've got two masses, let's grab a couple over here. These are two 500-gram masses. If I put them on the balance, it should balance out. It should equal the same. They should kind of be level. That doesn't necessarily tell us what the actual value is unless you knew one of these, and that's oftentimes what people would do. Back in the day, you had a known mass or a combination of known masses, and if you were selling somebody something, let's say you were buying a certain amount of meat, you'd put the meat on this scale and you'd keep on adding masses to this side until known masses until it balanced out, and then you'd know how much meat you were selling them. So that's used to compare mass. A scale, what this does is you set this mass on the scale. It pushes that scale down a certain amount, and that gives you a weight. We might still report that as a mass. We might say it has a weight of 500 grams, but grams is actually a mass, not a weight. There is a difference. That difference comes with the idea of gravity. If I brought both of these objects to the moon, and I put both of these masses on here, they would still be balanced. They still have a mass of 500 grams apiece. However, instead of having a weight of 500 grams, because gravity is less on the moon, it would be pulled down less, and you'd have a lower reading on here. It'd be 1/6 of this, actually. So if we're talking about 500 grams, 1/6 of that, I don't even want to try and do the math. Gosh, it's embarrassing. I'm not going to try and predict what that would be. So, what I'm going to add on here is that weight depends on gravity, while balance like this, mass, actually I should say mass neglects gravity. We talked a little bit about that word neglect. Neglect just means that it doesn't take into account, or it doesn't matter. You have to say, I have a mass of around 110 kilograms. I have a mass of 110 kilograms on the moon, and on Jupiter, and on Saturn, on anywhere I go in the universe. However, my weight, that's how much I'm being pulled down on Earth, is around 220 pounds or so. Or 230 pounds, somewhere in that ballpark. That is different based on where I go. If I go to the moon, I'm not being pulled down 230 pounds, I'm being pulled down more something like, I think it's 40 pounds total or something like that. If I go to Jupiter, I'm actually being pulled down something more about like 500 pounds of force or of weight. So what I'm trying to get at, mass, this is how much stuff you have, how much you're made of, how many atoms make up an object. Weight is how much that object, how much that mass is being pulled down. Okay, the next slide that we talked about, so we took just one slide of notes, we didn't spend a ton of time on this, is the idea of newtons. Newtons are units of force, and that's sometimes synonymous with weight. I was just talking about my weight. My weight is a force, but not every force is a weight. When you guys were doing the inclined plane lab, when you were pulling those cars, you were applying a force, but you weren't applying a weight to it so much. So they're sometimes the same, sometimes different. Our units are newtons, capital N. And what a Newton is it's a kilogram meter per second squared. It means if you have a value of 1 Newton, it means that the amount of force being applied is 1 kilogram being accelerated at 1 meter per second squared. That gets a little bit clunky to be using those units, so we actually combined all of those into one new unit called Newton. That's named after Sir Isaac Newton, who came up with the idea of Newton's laws, really applying gravity. So we talked, one last thing I wanted to draw on here. Newtons are force, kilograms is a mass, meters per second is acceleration. Hopefully some of you might be familiar with the idea of F, force, is equal to mass, M times A. F equals ma. That's actually Newton's second law. Your force depends on your mass and how much your mass is being accelerated by gravity on Earth or gravity on the moon, whatnot. Okay, the last thing we did is we spent a little bit of time exploring, and depending on which class you're in, your class made more or less progress on this, exploring the idea of two people pulling on a spring scale. I'm going to see if I can demonstrate this. This may go terribly. Let's see if we can illustrate this. Since I can't see my camera, I have no idea if you are seeing this correctly or not, but you should see that there are two readings for force here. If I, this is a spring scale, if I'm pulling, got 1 Newton on this scale and 1 Newton being read on this scale. So in class I demonstrated with me holding this on one end and somebody else holding the other end. And if I pull with 1 Newton that way, there should be an equal and opposite force pulling that way. With 1 Newton, that's the equal part, opposite is the other direction. So it's just a little bit of a demonstration of how forces work. That's actually Newton's third law, the idea that for every action there's an equal and opposite reaction. And then we grab a sliding block and some masses, and if you take a look at that data table right here, what we did is we compared surfaces to each other, the smooth side of the block or the sandpaper side of the block, and then you pulled it on a table or on the floor or on the carpet and recorded those force values. So take this block right here, and it's going to be hard to do one-handed. I'll just use this one since this is here. Okay, so you put a mass on there, and what you're going to do is you're going to pull the spring scale to see how much force is required to pull this. So if I'm pulling this, you can see hopefully that it's taking about 0.6 Newtons as I'm sliding this along. And then, so up there on the data table, I'd write 0.6 Newtons on table and smooth surface. Now we're going to flip this to the sandpaper side. So now the sandpaper is on the table side. Put that same mass on here and pull this, and notice now it takes about 1.35 Newtons or so to pull that exact same mass. So we filled out that table. Like I said, some classes finished, some classes didn't. We're going to use that as an intro into a lab that we're hopefully going to start tomorrow with skateboards and talking about the force of friction with the skateboard. So please watch us. Hopefully it gives you an idea of an abbreviated version of what we did in class today, and I hope to see you all tomorrow. Bye.